Now, without proof, I want to talk about constraint qualifications that tell you when the duality gap is 0. So these establish conditions for 0 duality gap, or for strong duality to hold. And qualitatively, it looks like this. This is the set of problems for which strong duality holds. And that is the set, and this is now very qualitative, this is the set of convex problems. So we have a convex objective with convex constraints. And I mainly want to say that there is no one-to-one relation, but these sets very largely overlap. So there are few examples of problems that are not convex, and still you have 0 duality gap. One such example being the so-called trust region problem, where you look for the minimum of a non-convex quadratic function over the unit ball. So there are a number of conditions or of different ways of expressing such conditions for 0 duality gap. And one well-known set of conditions is given by Slater's theorem, which, however, only holds for convex problems. And it says, and I'm going to state it without proof, it says that given a minimization problem, where both the objective function and the inequality functions there's a total of m of them. Then strong duality holds under the following condition. If we can find an x from the relative interior of the domain D that I previously specified, the relative interior, it essentially means it's the domain without its very limit. Namely that the affine inequality constraints should hold. And the non-affine constraints, so the general inequality constraints, should hold strictly. So I make a distinction. All of these are inequality constraints. I have a total of m inequality constraints, but I now make a distinction. The affine constraints just need to hold, whereas the non-affine constraints, they need to hold strictly. Sorry, and before here, I forgot equality constraints, which I want to express like that. So, in other words, Slater's theorems for convex problem only says that we do have strong duality if we find a feasible point from our domain such that all of these conditions hold. And as an important special case, let's look at the linear program again. So in the linear program, we want to minimize C transpose X. This is a linear function. It's both concave and convex. So I can say, yes, my objective function here, F0, is convex. Subject to some inequality constraints. They just need to hold. They don't need to hold strictly because they are affine. And some equality constraints. This is a form to express a linear program, and this fulfills Slater's conditions. So we have zero duality gap, or we have strong duality for linear programs. Provided we find a feasible solution to this problem. Okay, this was assuming convexity, and now I want to take a step back and lift this restriction when talking about complementary slackness. This is a property that I invoked when we were talking about support vector machines. And it was one of the conditions that we used to find the dual expression. So on this page again, I do not assume a convex primal problem. However, I do assume that strong duality holds. And that we have primal and dual optimal points. X star and lambda star nu star. Then I can write that given this assumption of strong duality, the optimum value of my primal problem will be identical to the optimum value of my dual problem. And I'm inserting the definition here of the dual function. It's the infimum over x of the following. this was the first equation here was using the assumption of strong duality, and the second equation was just using the definition of the dual function. And now I'm using the property that the infimum must give me a value smaller than or equal to my optimum value. This comes from the property of the infimum, which means that if no matter what value x star I insert, this must hold. The infimum must be at least as low. And now I'm using again the property that lambda is non-negative and that my f functions are non-positive and the hi's are 0, to say that this expression here is upper bounded by f0 of x star. And if you now look, we have f0 of x star at the very left and we have f0 of x star at the very right. And that means that these inequalities here actually are equalities. And from that we can, from these equalities, we can deduce useful properties. So equality 1 tells us that x star is indeed the minimizer, or if there's several ones, then x star is indeed a minimizer. And the equality number 2 is even more interesting. This now gives us the complementary slackness. So this equality, so the last terms, are 0. So what we have is that the sum over I, lambda I, must be 0. But we know moreover that each lambda I times fi is non-negative, because the lambdas have to be 0, the inequality constraints have to be smaller than 0 at the optimum, which is feasible. And this is why this thing being equal 0 holds not just for the sum, but for each individual term. So I get that lambda I star times fi of xi star equals 0. And this, when we were talking about support vector machines, was the property that told us that either a point is on the wrong side of the margin, so the constraint is active, and in such cases the Lagrange multiplier had to be non-zero, or vice versa, if we had a 0 Lagrange multiplier, it meant that we were on the right side of our decision boundary or of the margin. Go ahead. Because so lambda I is larger than or equal to 0, and wait. Sorry, they are non-positive. You're right. Excuse me. This is larger than 0, and this is less than or equal to 0 for a feasible x star. So they are non-positive, and because each one of them has to be non-positive, this is why each individual term then has to be 0 if the entire sum is 0. Thanks very much. So this being 0 means we have two cases. Either the one or the other is 0. Yeah? So for lambda I star larger than 0, we can conclude that this constraint function must be 0. And vice versa, if the constraint function is less than 0, then or less than or equal to 0, then the Lagrange multiplier has to be 0. So Lagrange multipliers are all 0 except for those constraints that are active at the optimum. Okay. So this is a property that we will also need later in the linear programming part. The Lagrange multipliers are 0 except for constraints that are active at the optimum x star. There is no xi. Thank you. I start scattering indices around here. Okay. So we finally come to the Karush-Kuhn-Tucker conditions, which are a summary of many of the equations that we've seen before, with just a single addition, namely the gradient of the objective and the constraint functions, and thus these Karush-Kuhn-Tucker optimality conditions only make sense for differentiable functions. So we're looking at them in two different scenarios. In the first scenario, I assume that the objective function f0 and the inequality constraints and the equality constraints are differentiable. And I assume a zero duality gap. Here I have to assume it. On the next page, under slightly different conditions, it will follow. Now, since X star minimizes the Lagrangian, as we saw here, so we saw that X star was a minimizer of this expression here. We must have that its derivative vanishes at X star. So the gradient with respect to X of F0 evaluated at the position X star plus the gradient of my inequality constraints evaluated at X star plus the gradient of the equality constraints evaluated at X star has to be 0. And again, if you remember support vector machines, this is how we derived the dual, by building the Lagrangian, finding this extremum, minimizing with respect to the primal, maximizing with respect to the dual variables. Okay, I'm calling this equation 1. And we can now summarize the other equations that, or assumptions that we already made. So for the point to be feasible, we had to make sure that our inequality constraints hold. We had to make sure that the equality constraints hold. We had to request or to require that our Lagrange multiplier lambda be non-negative, the one that's associated with inequality constraints. And we had the complementary slackness, the newest one, which is lambda I star times f of I x star had to be 0 for the inequality constraints. So in other words, for any optimization problem, convex or not, for which strong duality holds, and which is differentiable, for any such problem, any pair of primal and dual optimal points has to satisfy these Karush-Kuhn-Tucker conditions. And the second scenario is probably the more interesting one. In the second scenario, I'm making slightly different assumptions. Namely, this time I assume that the objective, or that the entire problem is convex and differentiable. So I assume that F0, F1 to Fm, H1 to Hp, that they be differentiable and convex. Then we can easily show that if such a pair of x tilde, lambda tilde, nu tilde satisfies the Karush-Kuhn-Tucker conditions, then they are primal and dual optimal. And strong duality holds. So how can we see that? If I number these equations, this was 1, 2, 3. 4 and 5. So first 2 and 3 tell us that x tilde is feasible in the primal domain. They being feasible, I know that the Lagrangian evaluated at any x, but at the optimum values here, is going to be a sum of convex functions. Because note that I had assumed everything to be convex. So everything is convex in the variable x, in the primal variable. And one said that we are at an extremum. And if we're at the extremum of a convex function, it tells us that we have found an overall minimizer. So, you see, this equation number 1 said that we were at an extremum, and a convex function, the extremum of a convex function, and we just argued that it must be a convex function, is going to be the minimizer, or a minimizer, and this is why we can say that x tilde minimizes this Lagrangian over x. And I can thus write my dual as the Lagrangian of x tilde, because we just saw that it was the minimizer of x tilde, lambda tilde, and nu tilde. And using the definition, this is f0 of x tilde this should be lambda tilde, not star. Okay. Now, we said that we wanted to be feasible, so hi was 0 according to this equation 3. And this here was 0 according to complementary slackness, equation 5. Because we were assuming that these variables satisfy the Karush-Kuhn-Tucker conditions. So this is just f0 of x tilde. And so on the left hand I have the optimum of my dual, on the right hand I have the optimum of my primal, and they are the same. So overall we see that there is zero duality gap. And this tuple of x tilde, lambda tilde, nu tilde are primal or dual optimal. So this holds for any convex optimization problem with differentiable objective and constraint function, and this is what we used in the SVM. So in the SVM we just said that indeed our if you remember, you know, we had what our objective function looked like. We had a L2 norm of our normal vector on the hyperplane, and we had a sum of slack variables, so this was surely convex. The constraints were also convex, so that everything was differentiable, so that we could use these Karush-Kuhn-Tucker conditions, and they guaranteed us, or this page shows us that we were guaranteed to have a zero duality gap, and that using these conditions or fulfilling these conditions was enough to find primal and dual optimal variables. Great timing today. This is what I wanted to say about duality in general. So no matter whether we were talking about, well, we assume convexity in a few of these cases, but not everywhere. So many of these statements were very general, and we will now have a break. And after the break, I want to introduce linear programs and say why they're interesting. So what kind of problems you can express as linear programs, and then study geometrical properties of linear programs, and finally give an algorithm how to solve linear programs.